a conical pendulum rotates in uniform circular motion. If the length of the pendulum is 10 centimeters and it makes an angle of 15 degrees away from vertical, what must the speed of the pendulum bob be? Now, I'm going to start a little sketch of this here because even though I've got that great picture right there kind of showing this in circular motion, and hopefully you can see kind of like the circular motion is describing there. So this is just an object that if I let it go right here, it would just swing back and forth in one dimension, like in a plane, right? But if I maybe like pushed it in just the right way, it could maybe go in a circle that's actually horizontal below this ceiling. Again, if I just gave it the right kind of push right at the beginning, and that's what makes this a conical pendulum as opposed to an ordinary pendulum. So it's good to kind of, try to visualize like what is that picture saying there. But I'm going to again start my own sketch here. I'm going to kind of fill in the bob right there because I'd like to fill in some of the details that the problem tells me, like where am I going to put in that 15 degrees? Where am I going to put in the 10 centimeters? Well, I think the 10 centimeters corresponds to the length of the pendulum. So I could put that there, and I'm going to make a note here. It's pretty customary for the length of a pendulum to be symbolized with the lowercase letter L. So I'm going to say that L is equal to 10 centimeters, which is equal to 0.1 meters. Might be useful later if I like. But in this picture, to give me a helpful hint here, I've got some extra lines in the slide that I just brought in there. And it might be nice to do something like that here as well and to recognize, okay, if I bring in those kind of dotted lines here, whoops, okay. I might have gone a little too far there with that one. Okay, I need to get better at making dotted lines here, I guess. But in terms of those, I've got kind of a nice triangle there now, but I think I can identify 15 degrees right there. And that to me means like away from vertical, because if it was 0 degrees away from vertical, the pendulum would just be hanging there. So that's how I identify that angle. It might also be useful to recognize that if I draw another vertical line right here above the pendulum bob, there is also that same 15 degrees right there, and that might wind up being useful to me. Now, to answer the question of what speed must the pendulum bob be going in order for this to be like a reasonable and sustainable motion, I think I'm going to have to analyze the forces. So really, in that sense, in this topic, we're doing circular motion, but we're also bringing all the techniques we have for doing forces, including the free body diagram. So I'm starting the free body diagram here. There is the force of gravity. Now, recognize we have a centripetal force. Did I say that right? Centripetal acceleration, I should say, right? Not a centripetal force. Do I have a centripetal force? I've got a centripetal acceleration because this thing's moving in a circle. I did that deliberately because this is a pitfall that I've seen really, really commonly. If somebody thinks about this centripetal acceleration, it must be getting pushed towards the center. And then they put in a force in their free body diagram pointing in that direction. But if you ask the question, what force is there? What push or pull is there in reality that does that? Is there somebody with their hand doing that? And the answer is no. I mean, you have to give this thing a push initially in some way to make it do this, but once you let go, it will keep doing it, and the absence of drag forces would actually never stop. So there is nothing there that looks like it'd be responsible for a horizontal force here, but there is a thread or a string or something that this bob is suspended from, and there can be a tension force. And the rules for tension force is that the tension force points generally away from the system and along the direction of the string. So I'm going to put in, that tension force, I meant to make that a capital T, more like for tension. So F sub T is that tension force right there. And then maybe I'm going to start right here doing an F net equals MA. And then recognize, okay, so we have force of gravity plus tension force. So I'm just turning this into a vector equation that as a tool is going to help guide me through the rest of this problem. This is a skill we've really been honing in this class, is how to use these vector equations as a tool and how to develop that from the problem using these kinds of pictures that we draw. So it might be possible to do this with a triangle, but this is F equals MA. I'm going to do a component analysis here. I think that's what I'm inclined to do with this, at least. So maybe as a challenge, somebody could say, could I do it with a triangle? I find it more challenging when there's something involving acceleration in a picture. Even though there are only 3 vectors here, maybe there'd be a way to think about that. But I'm going to do components with this. And then maybe the tricky part, well, let me see. If I'm looking at the x components, gravity clearly does not point in the standard x direction. So I'm assuming here, since I haven't said anything different, a standard xy coordinate system. So the tension force, though, does have an x component. How do we understand that? And I'm just going to redraw here, maybe a slightly zoomed in or enlarged version of the tension force so I can look at its component triangle and make sure I understand things correctly. So it's going to have a vertical and a horizontal component like that. The vertical component naturally is for the y, and the horizontal component naturally is for the x. And in terms of this picture, based on this angle right here and the fact that the tension force has to be in the direction of the string, I think in this triangle it makes sense that the 15 degrees would be right there. And so that means like the x component of the tension force would be equal to whatever the magnitude of the tension force is, which I actually don't know. But since it's opposite to that 15 degrees, it's going to be sine of 15 degrees. Again, multiplied by that hypotenuse gives me that other leg. That's the part I want to put here in the x component. So I'm, again, using this equation as a guide. There was no f sub g, but here it is. I'm going to put f sub t sine of 15 degrees. What can I set that equal to? Maybe I can just set that equal to ma, but this is, I'm not sure if I'm being careful enough here. That is a centripetal acceleration. It has a direction. It's to the left. So there's one thing. I think I forgot to put some minus signs in here, but it's a centripetal acceleration, so I'm just going to throw in v squared over r, recognizing again that the centripetal acceleration is equal to v squared over r. That is like the big formula that we're kind of been looking at here for this chapter so far. So I've got that in there. Maybe I should have made both of these minus, because really the component of the tension force was also in the negative x direction. So if I really want to be explicitly correct, I could have made them both minus, but you know what, then they cancel. So even if I'd forgot, as long as I consistently forgot, it probably would have been okay. In terms of y direction, I think I'm going to get minus, I'm just going to throw in here minus mg already, because the force of gravity points down, has a magnitude of the weight, which is mg, and then it looks like the tension force has a positive component, and this y component is really going to be equal to ft, cosine of, I barely have enough space here to kind of squeeze it in, cosine of 15 degrees. So I'm just going to put a plus ft cosine of 15 degrees right here, and those two should balance out to 0 since there is no vertical acceleration there. Okay, that's the physics analysis. Wow, that gave me a whole lot of formulas and a whole lot of symbols, but maybe I can do something with it now, because I can take this second formula here, and since I have not a lot of space, if you need to take some notes and fill in your own algebra steps for this, feel free to do that, I'm going to say. But I think that f sub t, based on the y component formula, is going to be equal to mg divided by cosine of 15 degrees. So what I did there is I added the mg to the other side, divided by the cosine of 15 degrees. By the way, did I mention this is maybe a somewhat difficult and advanced example, but I just want to show everyone, really illustrate how there is no like centrifugal or even centripetal force. In this case, it's very clear that what is giving us a centripetal acceleration is maybe just a component really of this tension force. There's really gravity and tension there because of the objects that are involved. So that's part of my intention with this problem and doing it, even though it gets kind of hard. Anyways, I'm going to take that and plug it into the x equation, maybe with these things already cancel. I'm just going to make those pluses now to make it clear. So this is going in here. Let's see. So that's going to be mg over cosine 15 degrees times sine 15 degrees is equal to this. Sine over cosine is equal to tangent, so I'm just going to turn that into an mg tangent of 15 degrees is equal to m v squared over r. So like I said, I just want to be fair and say, even though I didn't call this an optional example, we've had one of those recently. In that sense, everything we're doing here is maybe within fair game, but this is a pretty hard one. It's kind of pushing the edge a little bit. So I just want to make sure no one's getting like going like, oh my gosh, should I spend all my studying time focusing on hard ones like this? Maybe not. Make sure you know the easy ones too, right? But this one does illustrate some things. Can we solve anything yet? What were we asked for? Anyone remember? We were asked for the speed. There it is. Tangent of 15 degrees I can calculate. G I can calculate. If only I knew R. Well, I do know L, this 10 centimeters, and R is really like this length right here. So R, I think, is equal to L times, I believe, that's sine of 15 degrees. In other words, that's equal to 0.1 meters times sine of 15 degrees, which now it's time for a little calculator action, I think. So that winds up being equal to like a 0.025888. Is that going to be enough? Yeah, that's probably enough right there. Hang on, 2588. I might have said one too many eights there. And that's still in meters. So that is the result there. There's more if you actually calculate it, but that's probably enough for me to report right there. And at this point, from this formula right here, I might recognize v squared is equal to, if I multiply both sides of that by r, it's g times r times tangent of 15 degrees, which implies that v is going to be equal to the square root of all this stuff. GR tangent. So like I said, the math gets a little fierce on this one. Could be worse, I guess. So at this point, I'm going to put in my calculator 9.81 times, I'm going to leave the units out of this because I'm running out of space, 2588 times a tangent of 15 degrees. And the way I'm going to do the units still slightly legitimately is I know this should turn out to be a meter per second because I didn't want to have to write it for each term in there. I'm pretty sure it all works out because this would have been a meter per second squared times a meter would give you a meter squared per second squared, but then the square root would bring those down to just a meter per second. So you can put all of that into the calculator and it winds up giving 0.2608, etc. But I think 2 sig figs is going to be good enough here. That's in meters per second. Let's go ahead and check it now before this video gets any longer than it already is. Oh, 26. Oh, but check out the units, right? I said meters per second in my answer. The slide is saying centimeters per second. So those are actually equivalent physical quantities. Perfectly fine to use a different unit in that sense.